We're going to talk about some notation related to index sets. The first two notations are going to be related to numbers, addition and multiplication. Then we're going to talk about some notation related to sets. And finally, we'll talk about some notation related to logic. So if you want to jump ahead to a particular section, that's the order in which the video is going to go, is numbers, then sets, then logic. So first we're going to look at addition. And the symbol for adding over some index set is this sigma symbol here. So let's let I be the index set 1, 2, 3, 4, 5. And A1 is 2, A2 is 3, A3 is 1, A4 is 4, and A5 is 1. Then writing the sum of A1 to A5 would be the sum, or sigma, of AI from I equals 1 to 5. So the starting point is at the bottom and the ending point is at the top. So start at 1, go to 5, and add AI. So if we were to compute this, the sum would be I equals 1 to 5 of AI, means A1 plus A2 plus A3 plus A4 plus A5, or 2 plus 3 plus 1 plus 4 plus 1, which is 11. If we only wanted to sum A2 through A4, you could write I equals 2 to 4 of AI. So start at 2, go to 4. This would be A2 plus A3 plus A4. And you can also write a sum over all indices in a subset of the index set. So say that J is the subset of indices, 1, 4, 5. Well, you can't write I equals 1 to 5 here because we want to skip 2 and 3. But we can say just sum over all the indices J and J of AJ. In other words, 1, 4, and 5, which is 2 plus 4 plus 1, or 7. So you can see how this could be useful if you don't want to have to write out a large sum, but you want to talk about it or write about it. Maybe in statistics you have 1,000 data points, and you can just write sum over all the data points D or something, rather than having to write out, well, the entire sum of like 1,000 numbers. And for multiplication, we use a capital pi. So this is a capital or a large pi. So in this case, we're going to take, for example, the index set I equals 1 through 6, and we're going to take A1 is 1, A2 is 2, A3 is 3, A4 is 4, A5 is 5, and A6 is 2. So if I wanted to compute the product of all the numbers, I could write it as the product from 1 to 6, which means multiply all the numbers from A1 to A6. So this product from 1 to 6 of AI is A1 times A2 times A3 times A4 times A5 times A6, or 1 times 2 times 3 times 4 times 5 times 2, which is 240. And just like with addition, we can multiply over a smaller range. So I could put I equals 2 to 4, which means start at 2 and go to 4, and we would have AI is A2 times A3 times A4. And once again, we can define a subset of the indices to multiply over if we don't want to multiply from like 1, 2, 3 to, or from some number A to some number B. So if we're skipping numbers, say we have J equals 1, 2, 4, 6, we can multiply over the AJ and write the product as the sum over J in the set J of AJ, which means multiply A1, A2, A4, and A6, which in this case would be 1 times 2 times 4 times 2, or 16. Now we're going to look at some similar operations with sets. So whenever we're going to take a union over some sets with an index set, we use a large union symbol, or this large cup symbol. And similarly, whenever we're doing an intersection over an index set, we use a large intersection symbol. So notice this intersection is just a larger version of the regular intersection symbol. And we're going to let I, in this case, for our examples, be 1, 2, 3, and 4. And A1 is just the point A, A2 is going to be the set AB, A3 is AB, ACD, and A4 is F. So if we take the union of all 4 sets, we would write that as the union from I equals 1 to 4 of AI. And that is just right here. The union from 1 to 4 of AI is A1, union A2, union A3, union A4. And plugging that in and evaluating, we get A, B, C, D, F. Now, let's say that we wanted to intersect over 3 sets, A2, A3, A4. we could write the intersection from I equals 2 to 4 of AI, which would be A2 intersect A3 intersect A4. And if we want to intersect over some subset of the index set, say we want to intersect 1, 2, and 4, so we can't write from 1 to 4 because we're skipping 3, then we can define the set J as the subset 1, 2, 4, and just say intersect over all J and J. So of course this notation doesn't have an ending point, it's just saying, and there's not really a starting point either, it's just saying intersect over the J and J. And in this case we would have A1 intersect A2 intersect A4, or A intersect AB intersect F, which is empty. Now we're going to talk about doing logical operations over index sets. So the two operations are and and or, and for the and symbol we use a large and for the or symbol we use a large or. And we can also do exclusive or, so you just use a large exclusive or symbol. So let's let I equal 1, 2, 3, 4 be the index set, and the first statement is P1 is true, P2 is true, P3 is false, and P4 is true. So let's say I wanted to take the conjunction of all 4 statements. We could just write this large conjunction symbol, or this large and, from I equals 1 to 4 of Pi. So that means if I'm going to start at 1 and go to 4, it's P1 and P2 and P3 and P4, which is true and false and true, which equals false because there's at least one false. If I wanted to take the exclusive or over the AIs, but only going from 2 to 4, I would start at 2, so put in I equals 2 and end at 4. And that means A2 exclusive or A3 exclusive or A4, so this only goes from 2 to 4 and skips 1. And if we want to take an operation over a subset of I, some subset of the index set, we could let J be that subset. So say I want to take the OR operation, the disjunction of A1, A3, and A4. So I could say J is 1, 3, 4, and take the disjunction over J and J of the AJ, which means A1 or A3 or A4. So that skips over 2, rather than writing J equals 1 to 4. And this is true or false or true, which is true, because there's at least one true.